Okay, who can tell me the goal of this section? Like, what are we trying to learn, or what are we trying to do in this section? What is our goal here? Okay, yes, so we are using mean and standard deviation to describe our data, right? Okay, we have a two rule to describe the data. We have okay, so we had Chebyshev's rule and empirical rule. We use Chebyshev rule for any type of data. Okay, any type means if we have asymmetric or if our data is not symmetric, we can use our Chebyshev rule. But if the data set is symmetric, okay, data set being symmetric means the mean and median of that data set is equals to each other. So if we have a mean and median of a data set equals to each other, we call it symmetric data set. If we have a symmetric data set, we use empirical rule to describe the data set. Okay. Okay. So one more. So whenever we draw a let me draw a curve here. So for example, we have this curve here. Now, what is this for us? What it tells? Like, so you have this curve. What does it tell us? Do we have enough information whether this is symmetric or not? How can you say it's symmetric? So if we have a curve like a bell shape, that's the one way to know whether it's a symmetric or not. Okay. Now, what is this curve? Like, for what we have been using this curve? What it describes? What it tells us? Okay. So, not this. Okay. This one looks skewed, but what is this in actually like? This is the. Yes, it's a histogram of what? Of a data, right? So we have a data set, we draw a histogram, and how so our histogram, like in general, histogram has a bar, right? Like how we end up having a curve, the smooth curve instead of bar. Why we didn't draw like a bar to represent histogram? Why we are using this curve? So this is a histogram, that's correct, but it does not look like a histogram. Does it look like a histogram? Like like our histogram looks like this, right? So we have a class, and on each class there is a bar, okay? So this is the histogram. How did we end up with a smooth curve to represent histogram? Any guess?
The X-bars?
Can
The X-bars? Like the averages?
No.
It's like follows the skewness of the graph.
No. Now here, so our histogram always has a bar. Okay, we always use a height of bar to represent the frequency of a class or a relative frequency. Now when we construct a histogram, okay, with a bar of a very small width. Okay, now here, so we have, this is the width of the bar, okay? Every bar has a equal width. Now if we decrease or if we take a small width, okay, now our histogram appears to be a smooth curve, okay? Now here, whenever I draw this smooth curve, you should understand that this is a histogram of a data set, okay? Now to get this kind of a smooth curve, we must have a class of a small width, okay, small class size. For example, if your class size is of like 0.1 to 0.2, 0.2 to 0.3. So if the class size is very small here, right? And when you draw a histogram in a small class size, your histogram appears to be a smooth curve, okay? And this is like for now it's easy to draw, or it's easy to represent histogram with a smooth curve as well. So this is our histogram. Okay, now in this section, we are using mean standard deviation to describe our data set. Okay, now here we have 100 measurement. Okay, each measurement is the mileage rating for 100 cars. Now, in order to describe this data set using mean and standard deviation, what are we using? We are using a class interval, okay? So we want to calculate the number of measurement within one standard deviation. Now, how do we write that interval within one standard deviation of a mean? What is that? How do we write that mathematically? That is x bar minus s to x bar plus s. And like as in your class activity, we can rewrite this as so this is same as x bar plus minus s. Okay, do not get confused. These two are the same thing. Okay, so you can use any of this notation. Both of these represent standard deviation within one standard deviation of mean. Okay, and two standard deviation of mean, that is x bar minus 2s to x bar plus 2s. Okay, we can rewrite this as a x bar plus minus 2s. It's the same thing. And we want to know the number of measurement within three standard deviation of a mean. So that is x bar. So we want to know the number of measurement between x bar minus 3s to x bar plus 3s, and which is same as x bar plus minus 3s. Okay, now here can we switch can we write x bar plus 3s on the left and x bar minus 3s on the right? Is it still same thing? Like if I rewrite this as x bar plus 3s to x bar minus 3s, is it same thing? How many of you think these two are same thing? Raise your hand. Let me see. How many of you think these two are same? 1, 2, 3, 4, 5, 6. Okay. Now let me give an example. Okay, for example, so these are an interval. So if you have an interval 1 to 5, now is this same as interval 5 to 1? Is it same? Do you still think these two? Okay, these two are same thing. Okay, these are not same. Okay, now can you give me a number in this set? 4. We can find 4 in between 1 and 5. Now, can you give me a number in between this? Now, is it possible to have this kind of number? So here, how we read? So this is a set of number greater than 5 and less than 1. Do we have a number greater than 5 and less than 1? You have to have a number which is greater than 5 and less than 1. That is not possible, right? We don't have any number. So this is not correct, okay? So make sure to have your negative expression, okay? The small number on the left and the big number on the right. So every time if you are writing an interval, small number is always on the left and the bigger number is always on the right. Okay, so here we are trying to find the number of measurement in these three different interval. Okay, and you should be able to write this interval. Okay, there it does mention in words. This is one standard deviation within one standard deviation of a mean. This is two standard deviation of a mean. This is three standard deviation of a mean. Okay, now we have this 100 measurement. Let me give you mean. So our mean for this 100 measurement is 37. X bar is 37. Standard deviation for this 100 measurement is 2.4. Okay, 2.4. Now let's calculate the number of measurement within two standard deviation of a mean. Okay, so let's calculate number of measurement within two standard deviation of a mean. So within two standard deviation of mean, that is x bar minus 2s to x bar 2s. So at first we need to find this interval, okay? Now x bar is given as 37 minus standard deviation is 2.4 to 37 plus 2 times 2.4. And this is 37 minus 2.4 times 2, that is 4.8 to 37 plus 4.8. Okay, 37 minus 4.8, is it 32.2? 32.2 plus 0.8, 33 plus 4, 37. 37 plus 4.8, that is 41.8. Okay, just correct me if I'm wrong here. 37 for 41.8, right? Okay, now we have this interval, okay? So this interval tells that we are looking for a number which is greater than 32.2 and less than 41.8. Now we will count a number of measurement which is greater than 32.2 and less than 41.8 from this data set. Let's see how many measurements we can find. Okay, we can find this one, right? 32.7, yes. 40.5, yes. 36.2, 38.5, 36.3, 41, 37, 37.1, 39.9, 36.8, 36.5, 36.4, 38.2, 39.4, 36.6, 37. I think we're gonna have a lot, except this. Do we have any smaller number than 32.1? That would be easier for us to look for the smaller number here. 32.1. Okay, 32 point. So that is the only one smallest, right? Now, do we have something bigger than 41.8? Instead of counting.
The 30 in row.
Oh, is it row 2?
Yeah, about halfway there.
Row 2 or column 2?
Oh,
Okay. So we have this 30, right?
so then there's 31.8, like 4.
Oh, okay. Thank you. 31.8. Let's see. Then okay, 40 is, this is not included. 44 is not included. So out of 100, only 4 measurements are not here, right? It means how many measurements are in between these within 2 standard deviation of a mean? 96. Okay, and what is the percentage? 96 by 100. There are 100 measurement times 100%. So this gives us 96%. So 96% of the measurement is greater than 32.2 and less than 41.8. Okay. In the similar way, you can find the number of measurement within 1 standard deviation of a mean, and you can find the number of measurement within 3 standard deviation of mean. Okay, you will be asked to find the number of measurement within 1 standard deviation, 2 standard deviation, and 3 standard deviation of mean. Okay. Okay, so for this, does anyone have any question here? Okay, now. So let's see the details for this data set here. So what's given to us here is that the range for this 100 measurement is 44.9 minus 30. How do we find range? Largest measurement minus smallest, right? So 14.9 is the range. Okay. So the next thing, I want to add one more here. We can use range to approximate the standard deviation of our data set. Okay, now it's easier for us to find the range instead of standard deviation, right? Now, for example, if you are asked to find the standard deviation for this 100 measurement without using calculator, it's gonna be tough. I mean, it's not tough, but it's gonna take time, right? So whenever we have a large measurement, we can use range to approximate this standard deviation. We may not get exact standard deviation, but we can use that approximation to find the standard deviation. Okay, so here So the range for this 100 measurement is 14.9, okay? And if you divide range by 4, so if you divide range by 4, it gives us close approximation of the standard deviation. Okay? So finding range is the easiest one. You subtract the largest measurement and the lowest measurement, you get the range. Now you have a large measurement and you need to find the standard deviation. Okay, what you can do, instead of calculating the standard deviation, you can use this approximation. It means you divide the range by 4 and that number is close to the standard deviation. So what is 14.9 divided by 4?
3.725.
So this is 3.725. So this is the approximation. Okay, you can also use this 3.725 for a standard deviation. But we know, so for this, okay, now it has a standard deviation 2.4. Okay, this is the real standard deviation. Yes.
Further down it says that you can divide by 4 or 6, and when you divide by 6, it gets closer to the standard deviation. So why?
Okay, now here's the thing. So you can, okay, now, so what value do we get if we divide by 6?
2.48.
2.48, right? So we can write, okay, so here you can use, so the range divided by 6 to range divided by 4. So our standard deviation will be from 2.48 to 3.725. Not the minus, I'm going to have a. So when we use this approximation, so like in this data set, our standard deviation is very close to R over 6, right? 2.48. But in general, okay, so if we are talking, or if you want to use a general rule, then you divide range by 4. Okay, it's not wrong if you use, or if you divide range by 6. It's not wrong. Okay, now for this measurement, our standard deviation is very close to R over 6. Okay, but if you want to use a general rule to approximate a standard deviation or to find the approximation of a standard deviation, you divide range by 4. Okay, once you have this range divided by 4, you get a number, and this number in general is close to standard deviation. You can use this number for a standard deviation for this 100 measurement. Okay, so sometime you may not, so you might have a large data set and you may not be given a standard deviation. So don't go for calculating standard deviation. I want you to calculate range and divide that range by 4 and use that number as your standard deviation for given data set. Okay, so there might be a question where you need a standard deviation, but you are not required to find this standard deviation. You're gonna use this approximation. Okay, you are dividing the range by 4 to get a close approximation of the standard deviation. Okay, does anyone have any question up to here? And it's not wrong if you divide your range by 6, okay? That's still correct. So we get our standard deviation. So it's more precise, okay? Like for example, so you find range divided by 4, you find range divided by, range divided by 6, range divided by 4, you get an interval, and your standard deviation will be here, will be within this interval. Okay, so it's okay. So it's not wrong if you divide by 6. But the general rule is that we divide range by 4 to get a close approximation of the standard deviation. Okay, that's what I want to add here. And I think with this information, you should be able to solve is that part D of your class activity. Okay, so you're gonna need this concept. Okay, now one more. Let me make a revision here. So we have this histogram. Now from this histogram, what is the type of data set here? Symmetric. It is a bell-shaped. So this is a symmetric. Symmetric means mean and median are equals to each other. Okay. So now where will be our mean and median? So this is a symmetric. Mean and median are equals to each other. Now where do you write your mean and median? Yes. How do we know it's in the middle? Since mean and median are equal, right? Our median is always at the center, right? Median always divide our measurement into two equal parts. So our median is at the center. Mean and median are equals to each other. So at center we have mean. Okay, and this is true only if our data set is symmetric. If you have a bell curve, if you have a bell-shaped histogram, then mean is always at the center. Okay, mean is equals to median. Median is always at the center. Okay, and since our median and mean are equal, mean is also at the center. So this is our mean at the center. Okay, now let's talk about one standard deviation. So one standard deviation is you go one standard deviation to the right. Okay, this distance is 1s. You go one standard deviation to the left. Okay, now we have this interval. Okay, so we have this length here. So this is our interval, one standard deviation of mean. And what is this value? So this point is x bar minus s, right? Do you all agree? X bar is a number. You are going s distance to the left. So this is x bar minus s, and this is x bar plus s. Now, according to empirical rule, what percentage of measurement is within one standard deviation of a mean? Is it according to empirical rule, what percentage of measurement is within one standard deviation of a mean? 68. So it means, so the measurement that we find in between this point, okay, so here, so from here to here, we find 68% of the measurement, okay. So let me set this region. So this region is 68%, okay. So we have 68% of measurement in this region. Now, two standard deviation. So you go two standard deviation from mean. Okay, you are starting from mean. So you go 2s on the right, and you go 2s on the left. Okay. So we have this length, and this length is two standard deviation of a mean. So this point is x bar minus 2s. This point is x bar plus 2s. And what percentage of measurement do we find in between within two standard deviation of a mean? 95. So this region, okay, this region is 95%. Now we have three standard deviation. So you go 3s from mean. So you go 3s, okay, on the right and 3s on the left. So this point is x bar minus 3s. This point is x bar plus 3s. Okay. So we have this region. Okay, so from here to here, what percentage of measurement do we find here? Is it 99.7? Okay, so this region is 99.7. So 99.7% of measurement is here. Now, what about the remaining percentage of the measurement? Where do we find them? We might find on the right side or a left side or a both, okay, away from the three standard deviation of a mean. And we'll be talking about the outliers in our next section 2.7. So if we have a measurement out of these three standard deviation of a mean, we call them outliers. Okay, now does anyone have any question here? You should be able to draw this one, okay? You don't need to memorize those rules. Those rules will be given as a formula sheet. But you should be able to draw this one. And with this concept, we can use this concept in our real life problem here. Okay, now let's go to our next example. So here, a manufacturer of automobile batteries claims that average length. Okay, so here we have an average length of life for its grade A battery is 60 months. Now, what is this 60? How do we write this 60 months? What is this 60 months for us? Average length, which is x bar, right? So x bar is 60 So 60 months is the average life length for a grade A battery. However, the guarantee on this brand is 36 months. Okay. Suppose the standard deviation of the life length is known to be 10 months. Standard deviation of a life length is 10 months. How do we write using notation? S equals 10 months. And frequency distribution of the life length data is known to be mount shaped. We have a mount shaped. What does that mean for us? What is the type of data here? It's a symmetric. Now, if the data set is symmetric, what is the histogram? The histogram is a bell shaped, right? So you draw bell shaped histogram. Okay. Now, where do we find that 60? Where do we locate that 60 in this histogram? In the middle. This is symmetric. This is mount shaped. So, mean is at the middle. So, x bar, which is 60. Okay. So, this is x bar. And we are given with, standard deviation is 10. Now, let's construct one standard deviation of a mean. So you go 10 on the right. So this is 70, right? And you go 10 on the left. So we have 70, we have 50. So 50 to 70 is one standard deviation of a mean. Okay? Two standard deviation. So what will be this one? Yes, so this is gonna be 80, this will be 40, right? You know how we find this? So the formula is x bar minus 2s, 2x bar plus 2s. X bar is 60. 60 minus 2 times 10, that is 40. 60 plus 2 times 10, that is 80. Okay, what about 3 standard deviation? So we have 90 and we have 30. Okay, now does anyone have any question up to here? Do you all understand how we have a bell shaped here? What was the keyword they used here? How did we know that this curve gonna be bell shaped? It mentioned mount shaped. Okay, so this mount shaped or asymmetric, it is because of this we are using a bell shaped here. Our data is symmetric. Now the question here, approximately what percentage of the manufacturer's grade A batteries will last more than 50 months? Okay, now we want to know the percentage. Okay, the percentage of the manufacturer's grade A battery that lasts more than 50 months. Now, more than 50 months means what are the months? So we are looking for the months which is more than 50. Now, where do we find those months here? So our 50 is here. So we know our 50 is here, right? So more than 50 means, do we go on the right or the left? We are looking at the right. Okay, so our 50 is here. So we want to know the number of measurement on the right of 50. Okay, all the way to the right. So we want to know what percentage of measurement is greater than 50. Now this is a symmetric data set. If the data set is symmetric, which rule do we use? We use empirical. Now according to empirical rule, so this is our one standard deviation. So this is our one standard deviation, right? Do you all agree this is one standard deviation, 50 to 70? Now what percentage of measurement can we find within this one standard deviation of mean? 68. So we know this yellow region is 68%. Okay. Okay, before this one, okay, let me add one more thing. So what percentage of measurement do we find on the left of 60? So what percentage of the measurement do we find on the left of 60? 60 is our mean, okay? So let me draw one. So here, this is our bell shaped, our mean is here, okay? So what percentage of measurement do we find on the left of X bar? Do you all agree it's a 50%? Yes, this is symmetric. Mean and median are equal, and mean always divide our measurement into two equal parts, right? So we have 50%. So this region is 50%. Okay, so we find 50% of measurement on the left. And what percentage do we find on the right? 50%. Okay, and the total makes 100% of the measurement. Okay, so this is 50%. Now, in the similar way, can you tell me what percentage of measurement do we find on the right of 60? What percentage of measurement do we find on the right of 60? It's 50, because 60 is the mean, okay, which is the median. So this region is 50%, okay? So here, this region is 50%. So this is 50%. Okay? Now, what can you say about these two regions? Okay, not this. Okay. So what do you think of this region? Okay, let me call A1 and this region A2. What do you think of are these two related, A1 and A2? What do you think here? We know the graph is symmetric. Now, if that is the case, 50 and 70, they are at the same distance from 60, right? If that is the case, what will be, how A1 and A2 related to each other? Is it half of each other, or are they equals to each other? A1 and A2 are equals to each other, right? Because our graph is symmetric. Okay, and 50 and 70, they are at the same distance. So our A1 and A2 is equals to each other. Okay, so A1 is equals to A2. Now we know A1, when we add A1 and A2, the percentage is 68. Now what should be A1, or what will be A2?
34.
It's going to be half of 68, right? So this region, okay, this region is half of 68. Okay, half of 68, with 68% divided by 2, which is 34%. Now, can you tell me the percentage on the right of 50? What percentage is on the right of 50?
Or 50.
No, right of 60 is 50%, okay? So here, so from 60 to right, it is 50%, right? Because 60 is median, 60 is mean. And this region is 34. Now, if you add this region with this region, we get the total region, right? And the percentage on the right of 50 will be 50 plus 34, right? Which is 84%. So the percentage of a grade A battery that lasts more than 50 months is 84, which is 50 plus 38. 50% plus 38%, which is 34, not the 38. 34, and that is 84%. So there are 84% of percentage of the batteries that last more than 50 months. Okay, any question for part A? Okay, so now the next question, approximately what percentage of manufacturers' batteries will last less than 40 months? So less than 40 months, so our 40 is here, okay? Now, where are we looking at? Are we looking on the right of 40 or left of 40? Left, right? Because we want to know the batteries that last less than 40. It means we want to know the percentage on the left of 40. So we want to know what percentage is this region. That's what you want. Okay? let me draw one new graph here for part B. So we have 60 here, okay, that's 50, 70, 40, 80, 30, and 90. So we want to know the number of measurement on the left of 40. So our target is finding the percentage of this region, okay. Now how are we gonna find here? We will be using empirical rule, okay. So we all know what is this area. What is this area? Or what is this what percentage of measurement do we find on the right of 60? 50, right? So this is already 50. Now, so okay. Now, is there any way we could find what percentage is this in here? Okay. Okay, let me erase this one. So according to empirical rule, we know this region is, what is this region? 68%, right? And what percentage do we find in between 40 and 80? Who can tell me what percentage of measurement is in between 40 and 80 using empirical rule? 95. 40 and 80 is a 2 standard deviation of a mean, okay? So we have 95. So, okay. So this is 68, okay? And all this is 95. So all this region, okay, up to here, up to 80. So we have 95%. So this yellow region is 95%, okay. So our target is finding the green region, okay? We are trying to find green region. Now, how do we find? Okay, so here, let me get rid of this. Okay, what is this part? What is the area of this part? I mean, what is the percentage in this region?
47.5.
How did you get that?
95 minus 68 divided by 2.
Okay, that's right. So here, okay, now this region, okay, so this region and this region, they are equals to each other, right? How do we know that? So here, this is 40. So 40 is at the same distance from 60 as 80. So both of them are 20 distance away from each other, right? So these two regions are equals to each other, okay? So the number of measurement in this region, okay, and in this region has to be equals to each other. According to empirical rule, both of these two regions make 95%, right? So half of 95 is, so 47.5%. It looks more messier. Okay, so this is 47.5%. Now, can we find green region now? What percentage of measurement do we find on the left of 60? So from 60 to all the way to the left is 50%. From 60 to 40, that is 47.5%. Now what will be this region?
2.5.
How do we get that? You subtract the 50, the total 50% region from this red region, we get the green, right? So 50 minus 47.5. So 50%, okay, just let me. So 50% minus 47.5%. And what was the final answer? 2.5%. So 2.5% batteries will last less than 40 months. Okay? Do you have any question here? Okay, the next question here we have here is, suppose your battery lasts 37 months. What could you infer about the manufacturer's claim? Now, what is their claim? Their claim is their battery lasts, the guarantee given to this brand is 36 months, right? But your battery, you bought a new battery, okay, and your battery lasts 37 months. Now, what can we say here? So 37, where do we find 37? Okay, 37 is somewhere here, okay, and the guarantee on the brand is 36 months. Now, so you got a battery, okay, you got a new battery for your car. The guarantee time is, the warranty time is 36 months, but the battery stopped working on the 37th month. What will be your reaction? The warranty is 36 months, but it lasts 37 months. Now, like from this calculation, we know that 84% of the batteries last more than 50 months, right? So here, so now can we say the manufacturer's claim is not true? Is true. So then what is your case then? From here we know that 84% of the batteries, they last more than 50 months. But the battery that you got lasts only 36 months, so 37 months. Now, so here, so where does your battery belongs to? Now here, the battery that you got belongs to this percentage. It means the battery that you purchase is the 2.5% of 2.5%. Okay, it belongs to 2.5%. Okay, since we know so we have 84%, or like almost like more than 97.5, or like more than 96% of batteries has a life more than 40 months. But you got a battery and your battery lasts 36 months, means one claim we can make is that maybe manufacturer's claim may be false. Okay, like whatever data they provided, that may not be true. Okay, that's the one thing we can say. Or the other thing that we can say is that the battery that we got may belong to this 2.5%. So that's being unlucky, right? Sometimes it might happen. Okay, so like we can say two things. One is their claim may be false. Okay, other thing is that the battery that we got belongs to this 2.5%. Okay. Okay, so this is how we can use this empirical rule. Okay. Let's see if we can find one more very similar example. Okay, let's do this much for today. I will just make sure that we'll practice one more tomorrow. Okay, I'll bring a handout so it will be easier for us. So we still have 5 more minutes. So if you have any question, let me know. I'll be here for 5 more